Okay, so now we're going to look at things that might not be linear. So you got to think about, before we just decided it was linear or it was not, and if it was linear, we made a model. If it wasn't linear, we just didn't do anything because we couldn't do anything, basically. So basically, if it's a linear one, right, so choice number one, it's linear, right? You just do what we did in the last lesson, figure out the equation, make estimates. Well, let's say it's not linear, right? Not linear. Okay. At that point, you have three different options. Okay. Um, there, there could just be no relationship. That could be the case. Okay. It could be, you could make it linear. You could do what's called a re-expression, which means you're going to manipulate the data to make it linear. But that's not always possible. Or you could use a non-linear model, which we don't do. Model. Okay, so obviously we did the linear ones. They're already linear to begin with. If there's no relationship, that's always harder to tell, right? The non-linear modeling, that involves stuff that we don't do in this course. We are going to do the re-expressions, basically. We're going to take the data and make it linear. It means there is a relationship. We're just going to make it linear so we can model it with linear, basically. All right, so first is interpreting r squared. So this little link right here goes to r squared, and this is what we did before to calculate r squared in the prior lesson. Okay, so what does r squared tell you? So for this model here, the r squared value is 1, which means 100% of the y is accounted for by x, basically. So this one's a little bit worse. That's 83%. You notice that the values don't quite fit the model, which is the line, very well. That means only 83% of the y is accounted for by the x. And this one is 0, which is technically impossible. You can't get exactly 0. That means nothing in the y is accounted for by the x, right? So obviously you want to be closer to 1 and farther away from 0 for it to actually have some kind of relationship. Okay, so if we have this one here, 0.895, what is the interpretation of r? The hours spent at the university per day are 89.5% of the relationship of the number of lectures per day, right? Because there's other reasons to go to campus besides lectures, right? So the other percentage is that, basically. So look at fat and hamburgers. If it's 58%, right? It means 58% of the fat is attributed to the protein in the burger, obviously. So there are other ways to get protein other than just fat. Okay, that's the idea. There's another hurricane one. We'll skip that though. Okay, so let's think about the regression equation, right? Um, you want to make the linear regression fit reasonably well, the best as possible, right? You want the R to be significant, right, which we tested with the hypothesis testing in the previous lesson. And don't do extrapolation, which means go outside the data set. Okay, we'll talk about that why. If R is not significant, then the X value and Y value in the original model, you should not use that, basically. Okay, why is that my little y small? That's weird. Okay, so let's say we go from get the data prices from 71 to 82, right? And we have a model here, okay? Or do since 1970. So here's my model. Determine the predicted oil price in 1979, 1970, 1985. So if I wanted to do this, I would do P. So they sometimes use the hat or this for, which means predicted, basically, right? This is the predicted price. So actually, I write price maybe. Right. So price, right, is either a hat or this. Either one means predicted. It's not the actual price, the observed, right? So 0.68 plus 6.90. So if it's since 1970, if I go to 79, that'd be 9, wouldn't it? Okay, so what would be that predicted price? Okay, well, let's pop up my calculator here. A little slow. Oh, wrong screen. Okay, so if I remember correctly, there we go. Okay, Negative 3.68, that's not an 8, plus 6.9 times 9 is going to be $58.42, I guess, right? So $58.42. Okay, that's approximate, right? Because that's the predicted value. So we'll go out to 9 and 58 point something is probably right there. Oh, right there maybe. Oh, I'm sorry, right there. It'll be on the line. Okay. What am I talking about? Okay, so that is the predicted price, right? So that is the predicted, and that is the observed, right? And there's a difference between them, basically. So this is predicted, and this is observed, right? So the actual data is observed, and the what's on the actual line or the model is the predicted, right? And the difference between them is called a residual, right? You have a positive residual or you have a negative residual, right? So a residual is measured by E. I usually use E. That's residual. Residual, right? Which is observed minus predicted. Okay, and you either get a positive or negative residual, basically. So when you minimize those residuals, then you get the line of best fit. So then you have 70 and 85. Okay, which of these predictions are not valid? So obviously you put 0 in here for 70, and then 15 for 85, right? You should not do these two. One, this is the y-intercept, and you shouldn't typically do that because one, it doesn't usually make sense, and especially in this case, it's negative, right? And this is way past the data set. This goes only to 12, right? So 12 plus 70 is 82. So this is way past the data set. So you're talking about extrapolation at this point. So these are just different variations of extrapolation. This one's a very slight extrapolation. This is a massive extrapolation. So you should not do those. Okay. Let's think about why that is. Well, if you look at the actual price of oil, so I have the model here, and I have actually what it did, right? So should you use it? No, because the short term cannot predict the way out in the future necessarily very well. There's things you're not going to be able to attribute. You can only predict within the scope of your data, basically. That's why you shouldn't extrapolate. Okay, so how do outliers affect our modeling, and what should we do about them? Because we just ignored outliers completely in the last lesson. We just assumed there wasn't any, and we didn't remove any, basically. Okay, so if we look here. So an outlier is something by definition we did before mathematically, but here we're just going to do it visually, which means it has a high residual or high leverage. Okay, so look at the Buchanan and Nader votes in a particular place here. Those are two people that ran for office back in 2000. It's irrelevant who or what, but just get some good data. So what I have here is something with a large residual, because when I look at the model, okay, and I have two models here. There is the expected, this is the observed. It's a massive residual in comparison to the other residuals, right? So it's a comparison, right? So if all, because you want the best you want the line of best fit, which means it minimizes the residuals. So if all of these are within a certain range, and this one's clearly different than that by a large amount, it's a large residual. So that by definition, it is an outlier. Okay. So I forget which one is which when I did this. Okay, by omitting the observable outlier, which is this one, the regression model is this. Okay, so what you notice is it goes from 0.14 to 0.1, right? Okay, so now I remember now. So this is the model I did mathematically with the outlier, which is this one district they found, which was weird, right? This is how they actually do this to find things are going weird in elections. They'll do this to figure out what ones are weird. And once I remove that outlier, I get this one. Okay? So what an outlier does with a high residual is it's going to change the slope. Is it by a lot? Well, that depends what you're doing and how much that actually matters. The R squared was 0.42, 42%-ish, right? Jumps to 82. Okay? So that means the new model is probably more accurate. Okay. If Nader votes in this county, if you had 2,000 in, how did Buchanan have? All right. So if you plug in 2,000 to both models, obviously there'll be a change. By omitting the outlier, have a great effect on the model. Okay. So let's try. Let's put in the 2,000. So we'll go to here. We'll go to here. So 50.3 plus 0.14 times 2,000 and 50.5 times 0.1 times 2,000. Okay. Did I do that right? No, I didn't do that right. 50.5 plus, I don't know why that did multiply, times 2,000. Okay, so you have 330 versus 250. And these are the number of votes. So did it make a difference? I guess it depends. If it's New York City, that's not a lot of votes. If it's a small town in New Hampshire, that could be every vote in town. So it really depends. So did it make a difference? Yes. So at that point, it's kind of subjective as to whether it made a difference or not. But I would say definitely remove that as an outlier if you found that to be the case. Okay, so the other thing is leverage and outliers. We talked about the large residual. The other one is having high leverage. That can also mean it's an outlier. So leverage is a point that's far from the x values. So if you look at this one here, it doesn't seem to have much of a difference as far as residual. There's other ones with similar residuals, right? So it doesn't have a large residual, but it is far from the other values. Okay, so that means it has leverage, right? So think about this. If you're trying to take the bolts off your wheel, you have a long bar because the principles of leverage, right? Just like a seesaw. Okay, so you collect shoe sizes and IQ, and you graph them, right? But this is the guy who has the clown shoes, right? This is Ronald McDonald, right? So, so this person can have massive feet and be really smart, or massive feet and be really dumb. Notice what happens to the model, right? Because since these are all bunched up, it changes from a positive model to a negative model, right? So this is telling us that as you increase shoe size, your IQ goes down. This one says you increase shoe size, the IQ goes up. Is that really true? No. So again, when you have something with leverage, you should probably fill that one out also. Okay? So in both cases, you got 24.8. With this one, if you remove the point, you get 0.70 or 70% basically. Actually, put the other zero in there. Why not? Is this an influential person? Yes, because it's far from the data set. In both, does a person have, does it have a large residual in either case? No, it doesn't, right? It's about the same either way as other ones. Should you get rid of that point? Yes. Do they actually have a model? Probably not, but that's not really what we're answering here. Either way, I would remove it. So high residual, I would remove it, and high leverage, I would remove it. Okay, so all right, is the 2000 election exerting leverage? Well, let's go back. Is this exerting leverage? No, because it's not far from the data. Well, you're like, yeah, it's far. No, no, no. Left to right. This is X. Right? When you talk about leverage, you're only talking about X, right? Whatever the X axis is. Is it far from it? No, because these are the same X value. It does not have high leverage. If it was way over here, right, assuming it's talking about this graph, right, now it is far away from it, correct? You can maybe make an argument for this one, maybe, but definitely not this one. Okay, that has the same X value, right? So does it have high leverage? No. Does it have more or less effect on the model? Well, 40 to 70, or I'm sorry, 24 to 70, 42 to 81, so there's about a 40% change there. I don't know, about the same maybe? Who knows? Slight difference, obviously, but who's to say? Okay? Are they both bad? Yes, they're both bad. So what does it mean to be influential? Okay. If you vary different slopes. Okay, that's what it means to be influential. Okay, so I have three graphs here. Determine if it's unusual. Determine the unusual point. That's the unusual point. That's the unusual point. That's the unusual point. That's my opinion. Why? Does it have high leverage? Okay, well this one, x is far away from the x, that has high leverage. This is far away from the x's, that has high leverage. Okay, does it have a large residual? Yes. Has a high residual? No, because it's on the same line, right? So I do the line, does not have a, but again, I draw my line here. This has a massive residual, doesn't it? So it has a high residual. Okay, so that one has residual and leverage, high residual and high leverage. That has high leverage, that has a high residual. So residual, leverage, both. Is the point influential? Explain why. Well, this one is right on the line. That's not going to change the slope, right? So that's not influential, right? Not influential. Okay. Should you remove that point? Maybe. Is it going to make a difference? Not to the model, right? Should you remove this one? Yes. That is very influential because not only does it have leverage, you torqued on that wrench. Okay. This one has leverage, but you didn't torque on it, right? Just because you hook up the wrench to the tire to the lug nuts does not mean it's going to take the lug nuts off, right? You have to push down on that leverage on that bar to actually do something. So that high residual is really pushing it. So that's massively going to change that model. So this is the worst scenario possible. It has both. That has high influence, very high influence. Okay. This is going to have a small influence. You're like, wait a minute, but it has a high residual. Yeah, but it doesn't have high leverage, though. It's only one of many. It's like if you take 100 people and average their IQ, even if you have somebody with 150 IQ in there, it's not going to change the group by all that much. Will it change it? Yes. I would still remove this one and remove this one from the data set. This one is subjective, but these two you should always remove from the data set before making any linear models. So your linear model is y hat equals a plus bx, right? Or y hat equals a plus bx. Before you make that model, these two should be removed, right? You could probably get away with it by not doing this one and not getting a horribly wrong answer. This one won't change it very much at all, right? This has the most slope change, this has the least amount of slope change, and that's somewhat. So let's look at an example like this one. So let's go back to the Ralph Nader Buchanan one. So if you look at this, where is it here? Right? That's a very similar one where it has no leverage but high residual, right? Look what happened to the slope. 14 to 10%. Did it change it? Not very much, right? But you look at the slope here, massive change of slopes, right? So your higher leverage is going to change the slope more, basically. Unless it's like right on the line, it's not really going to matter. Okay. Lurking variables. So let's say we try to make it linear. So in the beginning it wasn't very linear, so we did some manipulation by doing like the square root of doctors over persons. We manipulated the x data, and we manipulated the x data TVs per person, right? And we modeled them to make them linear. So originally if you did life expectancy on the y-axis and doctors per person on the x-axis, it wasn't linear. But if I took the square root of it, it made it linear, right? And then you did TVs per person in life expectancy. It wasn't linear, but if I took the square root of it, it made it more linear. So I'm manipulating. So this is called a re-expression, right? So re-expression is when you change is when you change the x or y axis to make it fit a linear model, basically, because it wasn't linear to begin with. So then you can write your model, basically, right? So my model being y prime equals a plus bx, right? You're like, oh, okay. So these seem to fit well. They're going to get a good r squared value. I can make predictions using these r. But you got to think about the lurking variable, right? Things are not really thought of. You're just making assumptions on. Just because the math says it works doesn't mean that's actually true, right? That's why having no relationship is hard to prove. So you would look at this and you would say, well, this tends to fit a linear model better than the doctor one. So TVs per person tend to influence the outcome more than doctors per person, right? Does it though? Right? If you kind of think about it, yeah, doctors per person over time, yes, that's going to make better, because obviously you don't want to wait one doctor per 1,000 people or something like that. It's going to be ridiculous. That's not going to be good, right? Increased doctors kind of makes sense. But why is increasing televisions per person? Well, obviously over time, healthcare's gotten better, hasn't it? Right? Whether it's my great grandparents, my grandparents, right? We figured out penicillin, right? How to treat cancer, all these different things that my great grandparents didn't have, correct? We didn't have radiation therapy, all that other stuff, right? So healthcare over time has gotten better. Also, when I was a little kid, we had black and white TVs, right? And then you only had one TV. So the number of TVs in the house has grown, and then now you have 4 or 5 TVs in the house. My house is 0, but I'm different, right? But nowadays, the average number of TVs. So over time, we went from 0 TVs in houses, right, in the turn of the 1900s, right, to after the year 2000, way more. So there's the lurking variable. Over time, the number of TVs increased, but it has nothing to do with the healthcare. It's just because technology has gotten better. But also, the technology of healthcare has gotten better. It has nothing to do with TVs. So even though there's a very strong association mathematically with a very large R squared, that doesn't mean it's necessarily a good regression, right? That's the lurking variable, right? Okay, it's something that's not explicitly part of the model. It's affecting what's actually going on. It's a changing technology over time. They're kind of related, but one has nothing to do with the other. Okay. Um, so long story short, I have the same data set twice here, and you should remove the outliers. It makes a big difference. Okay. Um, okay. That'll be in a